Good evening. Welcome, everyone. And Talieh, great to see you online. Thank you so much for joining us. I have the distinct pleasure of introducing Talieh, who, as you may have seen in her bio, works with TD Bank and as a data scientist. But, you know, she's going to be talking about fairness and algorithmic decision making. But what an impressive CV we've got. Having spent almost 10 years working in experience in AI through a variety of academic ventures and publications. As said, she's worked with TD. She's a former chair of the IEEE Women in Engineering Toronto section, and has a variety of publications, both related to modular simulation, speech signals, emotional recognition, ML classification, and just to round out things with something totally different, phosphorus removal and water treatment. So with both studying both here in Canada and in Iran, I'm really excited about what she got to say because the experience is absolutely phenomenal. Across a variety of different interests. And that's always really interesting when we bring in some of our data scientists and speakers at the TLMS to have individuals who really bring some interesting non-machine learning, non-AI experience to that. And I think Talieh is going to bring that through in spades. So without further ado, I'll hand it over to you. Thank you so much, as ever, for those on the call. Drop your questions into the chat and we'll collect them. And over to you, Talieh. Thank you so much.
Thank you so much, Stuart, for the introduction, and thanks everyone for joining this call. Let me share my screen with you. As Stuart mentioned, this talk is around fairness and bias in machine learning models, with more focus in finance domain. I should say 20 minutes is just enough to touch the surface on this topic. And I tried to squeeze as much information as I could, so sorry if I go too fast. In this talk, I'm intending to just briefly talk about some applications of ML in finance, give you some general definitions of discrimination and fairness, and what fairness in ML algorithms, like why it matters. What are different sources of bias in algorithmic outcome, how to measure algorithmic bias, and some of the bias mitigation algorithms. So as you all know, machine learning is making significant inroad in the financial service industry. Some of the common applications are process automation, which is one of the common applications of machine learning in finance. This technology allows to replace manual work, automate repetitive tasks, and increase productivity. Some of the examples are chatbots, call centers automation, paperwork automation, etc. Security threats in finance are increasing along with the growing number of transactions, users, and third-party integrations. And machine learning algorithms are very good at detecting frauds. Machine learning algorithms fit perfectly with the underwriting and credit scoring task as well, and they are so common in finance and insurance. So you train a model on thousands of customer profiles with hundreds of data entries for each customer, and a well-trained system can then perform the same underwriting and credit scoring task in real time and real-life environment. In algorithmic trading, ML helps to make better trading decisions. So the model monitors the news and trade results in real time and detects patterns that can force stock prices to go up or down. And then it can act proactively to sell, hold, or buy stocks according to its predictions. Machine learning algorithms are also widely used in banks for marketing and offering promotions and products. The applications of ML in finance are by no means limited to what I just mentioned here. And in fact, new applications are emerging every day. So algorithmic fairness, why it matters. Let me start by a quote from Stephen Hawking, which says, "Success in creating AI would be the biggest event in human history. Unfortunately, it might also be the last unless we learn how to avoid the risk." So although it's very exaggerating to me, but it has a very good and valid point. So it is very important to understand the risks of automated decision making. To understand that it is not only the function of accuracy, it is also the function of trust. So although finance domain can hugely benefit from modern machine learning techniques, but on the other hand, there are concerns that these algorithms can also introduce new biases or perpetuate existing ones. And considering all the potential high-value use cases, it is important to understand the trust around it. It is important for us as practitioners to talk about what is our responsibility and possible risk management strategies before we use these methods, these models in production. Some general definitions for the word discrimination is unfairly treating people just because they belong to a specific minority group. It means prejudicially treating an individual only because he or she is a member of a certain group or a category without considering the person's individual merit. It also means giving opportunities to one group while denying the same to another minority group. According to social sciences, there are mainly two types of discrimination, direct and indirect. Direct discrimination, which is also known as disparate treatment, can happen by mentioning the minority or disadvantaged group based on discriminatory sensitive attributes. For example, an institute does not lend a loan to a person just because he or she belongs to a minority group. And in case of indirect discrimination, which is also known as disparate impact, the minority or disadvantaged group is not mentioned directly. However, it can be identified using background knowledge. So, for example, an institute does not grant some loan to a person because he or she lives in a particular area. However, from background knowledge such as census data, it may be clear that the people in that particular area belong to a minority group. Direct discrimination is often intentional and directed towards individuals, typically on the basis of their visible traits, while indirect discrimination occurs via apparently neutral practices that considers personal attributes correlated with indicators of some of the discriminatory grounds, such as race or gender. Fairness can also be categorized into group fairness and individual fairness. So group fairness in its broadest sense partitions the population into groups defined by protected attributes and seeks for some statistical measure to be equal across groups. Individual fairness seeks for similar individuals to be treated similarly based on a metric that defines how similar two given individuals are in the context of a decision-making task. So the nascent field of fair ML aims to ensure that decisions guided by algorithms are equitable, and discrimination-aware data mining is particularly important when outcome involves making life-impacting decisions for people. Some of the examples in finance are credit or insurance scoring, lendings, mortgages, credit cards, etc. Giving promotional offers, access to some benefits, and etc. So as ML increasingly affects domains protected by anti-discrimination law, there is much interest in the problem of algorithmically measuring and ensuring fairness in ML. So this is a photo which I got from an online post. I'm not sure about the accuracy of it at all, but it shows an increasing interest in the field of fairness in ML. So what does algorithmic fairness mean? One important issue here is the lack of a concrete definition of algorithmic fairness. There are a lot of definitions, and sometimes research groups are not on the same page. And it's a challenge because when you don't have a clear definition, then how you can model it correctly. But we can say that the primary objective is to achieve a higher accuracy model while ensuring that the models are lesser discriminant in relations to sensitive or protected attributes. In simple words, the output of the classifier should not correlate with protected or sensitive attributes. And building such ML models become the multi-objective optimization problem, which the quality of classifier is measured by its accuracy and the discrimination it makes on the basis of sensitive attributes. The actual discovery of discriminatory situations and practices hidden in the decision records under analysis may reveal an extremely difficult task, and the reason for this difficulty is twofold. The first one is that the data and decision records are highly dimensional. Data is characterized by many multi-valued variables, and as a sequence, a huge number of possible contexts may or may not be the cause for discrimination. To see this point better, consider the case of gender discrimination in credit approval. So, although a person may observe that there is no discrimination in general when considering the whole available decision records, but it may turn out that it is extremely difficult for aged women to obtain loans. And this might conceal discrimination, and therefore all possible specific situations should be considered as candidates, consisting of all possible combinations of variables and variable values. And clearly, this is a huge range of possibilities which make the work very hard. The second complexity is due to indirect discrimination. So as I mentioned, often the feature that may be object of discrimination, such as race or ethnicity, is not directly recorded in the data. Nevertheless, those may be equally hidden in the data. For instance, in the case like even in this case, once again, it's a big challenge because there's a large space of possibly discriminatory situations. So it's difficult to highlight all interesting discriminatory situations that emerge from the data, both directly and in combination with further background knowledge, such as census data. So what are different sources of bias and unfairness in algorithmic outcome? It's important to understand this if you want to actually remove or mitigate those biases. Unintended discrimination can find its way into a ML system in various ways and at all parts of part of the process. We can categorize discrimination by cause. The first cause is data issues, and the second one is misspecifications. So let's go to the history of bias in training data. This is the most straightforward cause of discrimination, and it can be summed up by repurposing a commonly used phrase in computer science: discrimination in, discrimination out. It is easy for people in media or for an observer to say that, oh, that's an algorithm's problem, or that's a machine learning problem. But the reality is the model is trained on historical data, and if there is bias in the historical data, those are going to be perpetuated or in some cases amplified in the model, in the final model, and decisions which are going to be made accordingly. So if we think of our society as a data generating process, and we acknowledge that despite great process over the years, our data as a cultural echo still reflects systematic biases against protected classes, then we should not be surprised to find discrimination in our models. Another type of bias resulting from data is sample bias, especially undersampling, which is also known as low support or underrepresentation. Differences in sample sizes between groups mean that more represented group will dominate the learning algorithm. Underestimation is even more likely to happen in cases where the target variable is rare, such as credit default. Whatever the cause, low support of a group can lead to a total exclusion of this group in future positive actions made by the decision process, as the classifier may not learn about the positive behavior that characterizes that group. Dynamic environment. So the population characteristic can shift over time. This is a well-known machine learning phenomenon known as drift. If subpopulations change differently over time, that can introduce disparities. Misspecification is a common concept, is statistic, and is the idea of model misspecification, which can be described as the functional form or the feature set of a model under study not being reflective of the true model. For example, in input features, including or not including the protected attributes matters. Including the protected attributes might be useful in a predictive sense, but of course, this puts the system at a much higher legal risk. The misspecification of the target variable stems from the fact that a data scientist often has several choices on how to define a target variable. And the decision process itself can be subjective. Even if we assume that we can control for any apparent subjectivity, there still may be ambiguity. Biases in the target variable are especially critical because they are guaranteed to bias the predictions. But the target variable is arguably the hardest from a measurement standpoint because it's often a construct that is made up for a purpose of the problem at hand rather than one that's widely understood and measured. For example, creditworthiness is a construct that was created in the context of the problem of how to successfully extend credit to customers. It is not an intrinsic property that people either possess or lack. So perhaps the simplest approach to designing a fair algorithm is to exclude the protected variables and protected characteristics from the model. And this strategy ensures that the decisions have no explicit dependence on group membership. So this is called fairness through unawareness, and it states that an algorithm is fair so as long as the protected attributes are not explicitly used in the decision-making process. Despite its compelling simplicity, fairness through unawareness has a clear shortcoming, as some elements of the feature set, as I mentioned before, could be partially or strongly correlated with the protected attributes. And this may not be obvious at first, and in many situations, these proxies are considered very legitimate and, in fact, very informative factors on which to base decisions. So the need for expert domain knowledge in assessing the relationships between the protected attributes and the other variables in the model is very critical. So in other words, blindness does not work in this case. But why blindness in ML is so ineffective compared to human decision-making? So for example, when we are asked to do a blind review, we would do it like totally unbiased review. But in ML, bias is just a side effect of maximizing accuracy, and ML is much better at picking up the proxies in the data. And this presentation, algorithmic fairness, is discussed in the context of a supervised binary classification task. However, this can be extended to a multi-class prediction task or a regression. These are some of the notations which I'm going to use in the following slides. So A is a set of sensitive attributes. X is a set of other variables used in the model. X sub E is explanatory attributes, which are user properties on which it's deemed acceptable to differentiate, even if that leads to apparent discrimination on protected attributes. I'll explain about this later in the future slides, so it will be more clear. S is the predicted scores or probabilities. Y hat are the predicted labels, and Y is the ground truth. So how to measure algorithmic bias? Many works have gone on to formalize mathematical notions using measure algorithmic bias. And typically, these are framed around problems of classification and decision-making. Group-independent predictions require that the decisions that are made are independent or conditionally independent of group membership and have been frequently used as measurements for fairness in prediction tasks. Many fairness criteria have been proposed over the years, each aiming to formalize different requirements. And most of the proposed fairness criteria are properties of the joint distribution of the sensitive attributes, the target variable, and the predicted outcome. The first one is called independence, and this criteria simply requires the sensitive characteristic and variables to be statistically independent of the outcome. Independence also has been explored through many equivalent terms or variants, such as demographic parity, statistical parity, group fairness, equal acceptance rate, disparate impact, and others. And it simply means parity in the proportion of positive decisions in each group. Separation, roughly speaking, the separation criterion allows correlation between the predicted outcome and the sensitive attributes to the extent that it is justified by the target variable. This criteria is also known as equalized odds, and is equivalent to the equal false positive rate and equal true positive rate. For example, in a loan context, this condition means that applicants with a good actual credit score and applicants with an actual bad credit score should have a similar classification regardless of the protected group. The next criteria is sufficiency. A classifier satisfies this condition if for any predicted outcome subjects in both protected and unprotected groups have equal probability to truly belong to the positive class. And sufficiency is equivalent to positive predictive value parity and negative predictive value parity. So in the case when the output of the model is actually scores, not labels, then this condition is called calibration. And calibration means that outcomes should be independent of predicted attributes, conditional on risk scores. Calibration ensures that risk scores mean the same thing for all the protected groups. So for example, again, in a loan context, calibration means that among applications with a given risk score, the proportion who would default if given the loan is the same across different groups. And the last one is conditional measures. So one issue with the absolute measures is that the different protected populations of interest may be distributionally different over the domain of X, and that a portion of discrimination observed at the macro level can be explained away by other non-protected attributes. So we can control for the explainable portion of the group level discrimination by modifying the statistical parity to condition on some observed non-protected attributes. In other words, we try to decompose the total bias into some explainable portion and some unexplainable portion. I'll give you an example to understand this better. So consider credit approval discrepancies between two age groups. So at the whole population level, we may see differences, but after controlling over some legitimate attributes such as income, level of income, or credit score, we may see that there is actually no difference. So now the question is which metric to choose. So first I should mention that different metrics matter to different stakeholders. So there is no right definition. For example, the decision maker wants to know that of those that they have labeled high risk, how many defaulted their loans. So they are interested in predictive value. The defendant wants to know what's the probability that I will be incorrectly classified high risk. So they are interested in false positive rate. And the society wants to know, is the selected set demographically balanced? So they are interested in demography. So what is discriminatory and what is legal to use as an explanation depends on the law and goals of the anti-discrimination policies. So the final word is this: choosing the right metrics among these depends on the legal definitions and restrictions, as well as the specifications of the application and available data. So thus, the interpretation of the attributes needs to be fixed externally by law or some domain experts. And when non-discrimination needs to be enforced, the law sets the constraints while we build the techniques to incorporate those constraints into classification. Otherwise, the selection of explanatory attributes become very confusing and debatable, because one reasonable explanation could be highly unreasonable for the other one. Another point that I should also mention is that whether or not these disparities are objectionable may differ between cultures and also may change over time as social norms evolve. Some methods and algorithms have been developed by researchers aiming at mitigating algorithmic bias. This field is referred to as discriminative or data mining. The discrimination-aware methods are grouped into three main categories based on the location where these algorithms can intervene in a complete ML pipeline. The first group is pre-processing algorithms. This group of methods attack the problem by removing the underlying discrimination from the data prior to any modeling. The second group are in-processing algorithms. And these techniques can be thought of as a modification of traditional learning algorithms to address discrimination during the model training phase. And the third group are post-processing algorithms. This class of methods can be performed as a post-training. Talking about these methods and algorithms are out of the scope of this talk, and they are all highly technical papers. Explainable AI is an adjacent field which adds more transparency to the black box AI models. Explainable AI is an emerging field in ML that aims to address how black box decisions of AI system are made and adds more transparency to how the decision is being made. And adding transparency to the AI system could be a complementary approach to inspect model biases. For example, these graphs and figures that I'm presenting here, they are from a method called SHAP, or SHAP values. So they can provide the ranking of the features according to their importance in the model, also provide the input-output relationship and how each variable affects the final decision. There are other methods available, such as partial dependence plot, LIME, and there are some other methods as well. And some open source tools have been developed, some for just detecting algorithmic bias, some for both detecting and mitigating those biases.
Hi, Talieh.
There are some reasons.
I'm
Yes.
sorry to interrupt you. I think we're running out of time for our next talk.
Yeah, sure, I'm done. So these are just some of the resources, and would be happy to take the questions.
Thank you for your talk. It was pretty insightful. So I'll directly jump into a couple of questions. So one of the question is, are the bias matrices tied to the specific model, or they are model agnostic?
They are model agnostic. They just depend. They depend on just the output of the model. Yeah.
Okay, and the second question is, are there any existing regulations that apply to finance with respect to fairness and algorithmic bias?
So basically, it's the compliance and legal department of each institution and banks which should set the thresholds and define what is discriminatory in each application. So depending on the risk level of the application, the the fairness requirements goes higher, and those are all set by the legal and compliance department. There's no set threshold or anything yet here in Canada. There are some in US, but nothing yet in Canada.
Okay, I think we have to wrap up this session in the interest of time. Thank you for your wonderful talk. I think we can meet with Talieh outside of the platform. If you have any other questions, you can take it with her. Thank you, Talieh.